Okay. You knew how to just plug these in? In any equation, you take your value of x, you plug it in, or whatever variable you have, and you make sure it works. Well, you have a couple of ways to do this. You could either solve it and see if your angles were in your solution, but the easy way is just to plug it in. This is a solution of your equation. So plug this in here. Put your mode in radians, plug it in, and see if when you hit that, it equals 0. And both of those worked, and in the other ones, they also worked. I did them out a couple of ways. You know, I wanted to show you work in there, so I plugged them all in and showed you that they work. But you can just put them in your calculator, just like you check any other equation, to see that works. Okay, now the good stuff. We talked yesterday, we did the equations side by side. Algebraically, you solve the equations. Once you get down to what a sine is, what a cosine is, you need to find the angles. So you come down here and you solve your equation. This does the algebra part right here. This is why it's called the trigonometric equation, because I want to know what angles have a sine of -1/2. Now start from your 0 to 2 pi. No restrictions on these. Sine is negative in 3 and 4. So I fill in my triangles, which I told you probably will not be getting rid of these for a little while. You've got a 1/2. There's a reference angle of 30. Find this angle, 7 pi. Find this angle, 11 pi over 6. Now, that gives us our angles from 0 to 2 pi. For all solutions, I want any coterminal angle. Another 2 pi, another 2 pi, another 2 pi. So I add 2n pi where n is any integer. A negative will just set me back in the other direction, and I'll find it. Okay, so that add 2n pi just gives you a series of coterminal angles forever. Because your sine curve, your cosine curve, your functions are continuous forever. Can we do this? Do we understand? And I'm not seeing it on some of your papers. You're getting down to here, but then all of a sudden you're kind of like stopping right there. So does everybody see it? Yes.
I just don't like the
Plus 2n pi. So let's talk degrees a second. Let's talk degrees. This is a 30 angle, so what angle is this in degrees? 210, right? Now, if I want another angle that's coterminal to this, I have to go around another 360 degrees and get there again, right? So if I add 360 degrees to this, my angle would be 570. Every 360 degrees would put me back at that angle, that same terminal side. So I could say 210 plus 360n, where n is any integer. I could multiply it by 1, by 2, by 3, by 4. But because we go into radians, there's your angle in radians, and there's your 2 pi. Maybe it would look better if we did this, 2 pi n. Every 2 pi n times. So at the 0, you would be that original angle. Then at the 1, you came around again, came around for 2, came around for 3. It would be many times around.
That's what you mean when n is any integer?
N is any integer. Because I could come around 8 times, right? It's endless. Your
Like
n number, any number that you want to pick. Your cycle of sine, when you make a sine curve, this just goes on and on and on and on forever and ever. So all your positive 1/2, or your positive or negative 1/2, all your negative 1/2 keep going on and on and on forever, don't they? They keep going on and on. So I could define them by using that little scenario. We keep it in radians, and maybe it looks better to say 2 pi n. And that might be better for you to qualify it. Maybe it makes more sense that way. Okay. This guy, solve it the same way. Here's your equation. Subtract 1, divide by radical 2. 1 and radical 2 should ring a bell with the special triangle. So I set up again where my sign is negative. I set up my special triangle, find my reference angle is 45, and I find both angles. The one that goes from here to here, and then any angle that goes back again, and back again, and back again. There's my 2 pi n if you like. And then this angle is a 7 pi. You only need one qualifier. If you just put it once somewhere down there, where n is any integer, that's fine. The bottom one, we add 2. You find this. Now, if this looks a little weird, take the reciprocal of both. It's an equation. Take the reciprocal of both sides. A reciprocal of the secant is a cosine. If you take the reciprocal of that, take the reciprocal of that one, the other side. Radical 3 over 2. That's one of your special triangles. Cosine is positive in 1 and 4. So find your reference angle, name those 2, and then plus 2 pi. Plus 2 pi. You got to be able to get to this part. You got to be able to find the angles. So did you write it down? Or your hand hurt? You can't write it down. Okay, you wrote this down on your blank page? Okay. Alright. So, now we're looking at cotangent. Cotangent has a period of pi of 180. So we have a nice little feature for cotangent and tangent. Notice, the sines and the cosines are always next to each other. Whether it's the side, the top, the bottom, the other side. The tangent and the cotangent are always across from each other. 180 degrees apart. So now, I can say, name this angle. So I name this angle here, which is 3 pi over 4. If I add pi to it, let's try degrees first. I name this angle, 135 degrees. I need to name this angle, which is 315. If I add 180 to this, don't I get to 315? Maybe you see it better in degrees. But we're keeping it in radians, so 180 is the same as pi. And I add another 180, then another 180, then another 180. Because they're opposite each other and their period is pi, I just need to say one of those angles, the first one, and n pi, where n is any integer. Good? Technically, if you said the last one, it would still work because I could go the opposite way with a negative, but we really don't like to do that. We like to pick the first one. Number 33 is a little unique. And by the way, my other group kept leaving this like this. But you're not going to be able to separate it if it's under the radical. And you're not going to build a triangle with this. Separate this. It's going to look more obvious to you. This is 2 over radical 3. If that doesn't look obvious, do the reciprocals. That looks better, radical 3 over 2. Whenever you undo a square, remember you get a plus or minus. Therefore, you get all 4 quadrants. And now you can kind of cheat a little. You can name this guy and do the n pi for this one. Then you can name this guy and do the n pi for that one. Because they're exactly across from each other. You could take all 4 and do the plus 2 n pi, but really the n pi's would work better. We have 4 angles that make it in 0 to 2 pi, but we want to keep a continuous run. Does this one make sense? Because I know this one confused my other group. If you leave it as radical 4 over 3, it's not going to make any sense. And you're never going to be able to get it into a triangle form. So remember to reduce your radicals to lowest terms. That's going to help you identify your special triangles. And you learned how to check it in your calculator. You can always take one of your angles, put it back in, and plug that in and see if it works. And that'll tell you that you're right. All your equations are checkable. So any of your answers that you get, because some of them look a little strange, plug it back in and see if it's working. Okay. These the last two? Okay, last two. Cotangent and tangent work the same. This one, when you take the square root, you get a plus or minus. So it's all four quadrants again. Name the first one, name the second one, and do the plus and pi. And the last one also used all four quadrants. And again, don't leave it as radical 1 over 4. Separate it. Because now 1 over 2 rings a bell with you. Cosine 1/2. Oh yeah, we know that. That's a 60-degree angle. And even if you forgot it, you can put it in your calc. Second cosine 1/2. 60 degrees. Questions on any of these? Just as you did this with the equations, and you took the words out and put a variable in there, if you have trouble seeing this, take the words out and put a variable in there. So, what two functions do you notice up here? Cotangent. Okay, let's make cotangent be an x right now. And let's make cosine be a y. And so that's going to have to be a square, right? So right now, I've got this. Okay, I need to solve for this thing. I cannot divide by a variable. So what should I do? Can't divide by x. Can't divide by a variable. That's the square root. Not divide by 2. Square it won't help me. Subtract. I'm going to subtract this guy to the other side. And then maybe now I can do what? What do they both share? X. So now I can factor. So now look what happens. Now I get both of my factors that have a different variable. I can solve them. And then you can add 2, take the square root, take your square root. Now, it always looks a little trickier with sines and cosines in there. So sometimes if you need to take them out, take them out. I can, at this point, I could go back in and say, my cotangent was my x. I could do this. My cosine was my y. I could absolutely do that and find my angles because you're just replacing them back, if that makes life easier. Or sometimes as soon as you just write it over to the side, you say, I know what I have to do. So I could subtract my cotangent, like Will said to do with the x's. So we subtract this guy. They both share the cotangent. These, yes, but can I factor out something out of there? They're two factors. They're connected as a product because they're two factors. And then I can just do this. Cotangent x equals 0. I can add 2 to both sides, just like we did over there. Square root. If you want to leave it in the other way, whichever way you prefer to see it. I find sometimes that it's confusing when you look at those because first of all, even with variables, that always throws everybody off. Everybody wants to divide by x, or divide by 2, or take the square root. You want to get everything on one side. Whenever you have descending variables, get them together. Okay, at this point, you can go find your angles. So if we need to solve this just between 0 and 2 pi, my cotangent was a 0. It had to come from one of these. My cotangent is x over y. Which one can I divide x over y and get a 0? Not the 0. The 0 will give me undefined. The 90, because isn't it undefined at the tangent? So shouldn't it be defined at the cotangent? If I take 0 divided by 1, isn't that 0? 0 divided by negative 1, isn't that 0? So I have two answers right here. Pi over 2 and 3 pi over 2. That gives me an answer to that one. If I was looking for all solutions, I would just need the 1. X equals pi over 2 plus n pi, where n is any integer, because aren't they 180 apart? 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, right? I'm just adding an n apart. Now, I finished that part. Let's go to this part. Add a cosine whose radical 2. What do you think about that? Okay, first of all, it's in all 4 quadrants. Let's break this down. This is x over r. Could that be a triangle? Radical 2 is approximately what? It's got to be bigger than 1, right? Because radical 1 is 1. Could a cosine be larger than 1? Think of your cosine curve. Where's the range go to? 1 to negative 1, right? So could I have an angle? Try it in your calc. Second cosine, radical 2. See what angle they come up with. My cosine cannot be out of the 1 to negative 1 range. What does it say? At a domain? Or what? What was the thing that says on top? Domain. It's out of your domain, right? It's not, that's the angle does not exist. So I reject this. And I have, well, from 0 to 2 pi, I have 2 answers. Okay? So we're going to factor them to the exact same point that we wrote last night's homework. We're looking to find where the angle exists and name the angle. And sometimes the angle doesn't exist. Sine and cosine can't be added to 1 to negative 1. Their reciprocals, yes, their reciprocals can't be in that range of 1 to negative 1. Okay, let's try another one. All right, so I'm not exactly seeing this yet, so I'm going to take this out and make this x squared. This is a sine, so that's also an x. So I have 2x squared minus x minus 1. How would I factor that? They're not perfect squares, but I do get 2 binomials because it's a trinomial, right? It's okay that a is not 1 because this guy is 1. What are factors of 1? 1 and 1. What are factors of 2? 2 and 1. Now all I have to do is worry about my little smile in the middle. Where do I put my plus? Where do I put my minus? So that the middle term comes out to be a negative. So if I put a plus over here, well, it has to go to the bigger number, but this time, this bigger number, it has to go over here. So that's your negative 2x. This is your positive 1x. Because the a wasn't the 1 this time. So there's my factors. Now, if you want, slide the word sine back in there. 2 sine x plus 1. 1 sine x minus 1. You're going to factor your trig just like a regular trinomial. You're going to set your factors equal to 0. So we're going to subtract 1 and divide by 2. Now, same as last night's homework. You have an angle whose sine is negative 1/2. Where is sine negative? 3, 3 and 4. Right. So sine is 1 over 2. What reference angle? 30. How many times does 30 go into 180? So this is 6 pi over 6. This is 12 pi over 6. Now watch. We only want to go from 0 to 4 pi. So let's think this out. This guy right here would be what angle? 7 pi over 6. This one right here in quadrant 4, 11 pi over 6. Let's go around this again. We just want 2 pi. Let's add another 6 pi over, we keep adding 6 pi, right? Let's add another 6 pi to this. What do I get? 18 pi over 6. And another 6 pi? 24 pi over 6. Isn't that the same as 4 pi? So now, using the 18, what angle is this? 19 pi over 6. What angle is this guy? 23 pi over 6. I only had to go, I didn't have to do the whole 2n pi thing. I only had to go to 4 pi. So just keep your pattern going. This one's 6, 12, 18, 24, 30, 36. I could do this a number of times. I only had to go from 0 to 4 pi. Okay? And you have to do it with this one as well. This is only part of it. Sine of 1. Anybody remember where the sine is 1? 90. At 90. Over here. Okay? Now, I'm going to have to add a pi over 2. I've got to go around again. It can't be at the 270 because that will be a negative 1. So this is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. All of these angles are my answers. And can I put them in and check? I can put them in and check. Because sine is only positive up here at the 1. When it's 1. This guy down here is 0, negative 1.
So then that's negative pi over 2 and 4 pi. So
We only have to go from 0 to 4 pi. Yeah, so count by a half. Right, no. Count the 1. Yeah, count the half. Then say this is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Now here I come back around. 5 pi over 2. It's the same as if you added 2 pi to that. If you took pi over 2 and you added 2 pi, you have to convert this to 4 pi over 2. That would give you your 5 pi over 2. But we just cheated and we counted it around ourselves. So we're seeing this? So all we actually did was just add factoring in, and then the rest of it stayed the same. Okay? One more. This one's a little tougher. This one, if I take this out and make this an x, I would have 2x squared. But I notice this is cosine. I have to make this a y. Could I factor something that has x and y's in it? Unless they both share something that I could take out. But they don't share the same term. So I have to find a way to substitute one of those sines or cosines. And you have one property that we discussed a while back with your Pythagorean identities. You have sine squared plus cosine squared equals 1. This is the one that's really helpful to remember. We did this in Trig 1. Probably like before Christmas. And if you solve for sine squared, you subtract cosine squared from both sides. you can substitute sine squared for 1 minus cosine squared. So I'm going to take this out and use 1 minus cosine squared. Just take this out and substitute it in. I got to keep the rest of my equation. So now everything will be cosine. Unfortunately, we have to collect like terms and do what we need to do. So we've got 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Put a line down that equal sign first, because you have to collect the terms on one side. So let's take your highest term, negative 2 cosine squared x. Take your next term, and you're on the same side. What does a 2 and a negative 3 give us? If you combine those, negative 1. Now, in order to factor this, you need a to be equal to 1. So let's divide everything by a negative 1. Where are equal signs? Is this wonderful? Just change the signs of everything. Now you can factor. Okay? So we're going to factor like this. 1 only goes 1 and 1. Look at your signs. What do they both have to be? I need to multiply and get a positive. I need to add and get a negative. Negative. So that's exactly the same. I only have one factor of 2 and of 2. It's a prime number. 2 cosine x, 1 cosine x. There's your factors. Okay? So I get a negative 2, negative 1. That gives me my negative 3. I set these both equal to 0. We're almost there. Add 1, divide by 2. And cosine x is equal to 1. Now I solve. Let's hit the cosine x guy. Whenever you have a cosine and a sine of a 1 and a 0, it came from a quadrant. So it came from right here. It came from your 0. Did we want this in 0 to, let's just go 0 to 2 pi. So your answer would be 0. If I needed to come back, I could be at 2 pi if you want to go to 2 pi and include that. Or 4 pi if we're going to 4 pi. But it depends if they write it, which way they write it. If they give you both parentheses, then you got to give me a 2 pi as well. Or if we're going to go to 4 pi, give me a 4 pi. And then cosine. Where is cosine positive? 1 and 4. So this is your 60 degrees. So what angle is this guy right here? Pi over 3. And what's this guy right here? Pi over 3? So let's just go from 0 to 2 pi, make life easy. Okay? This is probably one of the harder ones. You had to